All right. Welcome to the 7th lecture in the summer Haskell class. So, first of all, let me get this thing off my screen. So, I'm going to be away next week on vacation. And then I figure that'd be a good time to have like a 2-week break in the class for everyone who's missed a couple classes to catch up. The slides and videos are on the course page on GitHub, and these slides will be put up tonight, and then the video will probably be put up tomorrow. And if you are caught up and you're looking for more Haskell, by this point you're definitely at the level where if you understand everything that I presented, you can start attacking the intermediate level resources. So Learn You a Haskell is another beginner course. It's very similar to what I've done. Takes a little bit of a different approach. So if you want to reinforce your knowledge, that would be a good book to check out. Structure and Interpretation of Computer Programs is a Lisp book, but the second lab, which we're going to do when I get back, is based on a Lisp. So that'll just make it easier to understand what you're up against when you program a Lisp. The GitHub repository itself, ignore the file called lab2.hs. That's an approach that I took that was not quite as rigorous as what I'll actually be using for that lab. Instead, there's lisp.hs and the modules it brings in. That'll be finished probably within a couple of days, I'd like to say, unless I find some horrible bug or conceptual flaw. That stuff is almost done, and then I'll just organize it and make it more accessible. There's a resource called the Type Classopedia. It talks about the main type classes of Haskell, and it covers some of the ones I haven't covered yet, like foldable, traversable, semigroup, arrow. Some of those I'll cover later in the second half of the course, but it's a good resource if you want to see more type classes and more uses of type classes. There's a book called Real World Haskell. My only criticism, it's not really a criticism, it's 7 years old. So some of the web library stuff is out of date. It doesn't cover applicative because that was not really even invented until recently. I think the first paper came out in 2006, but it's a solid book, and I'd recommend reading it just to get a sense of what system programming looks like in Haskell. There are some larger code samples and projects that are worth looking at. By the way, all of these are available online. There are a couple books that are not available online that you could also look at, but everything I've put in these slides is available for free. There's a book called Parallel and Concurrent Programming in Haskell. That's pretty advanced, but if you want to give it a shot, go ahead. I'll be taking some material for the second half out of that book. I think it's a great book. It's probably the best book on concurrent programming in addition to being a very good Haskell book. It'll give like a blurb about this, a blurb about that. Some of it's fairly advanced, but it's very thorough. And finally, you should be sending me suggestions on what you want to cover in the second half, because I've got a little bit of it planned out, but there are some things that are pretty open. And once we've got the basic type classes down, it's sort of up to us what we want to do next. But today we're going to bear down on monad and applicative. Because to really understand these type classes, we need to know their laws. You know, we're not design pattern Java programmers who can just be like, oh, it looks like a visitor, so I'll call it that. They're actually laws. There are reasons why these type classes represent state and effectfulness. And to get a handle on that, we have to know how they behave. So these are the applicative laws. I'll go over each one and what they mean. Identity is the first. It says that if you apply, by the way, the snowflake operator, I've learned people just pronounce it as app. What?
F like
App.
oh app.
Damn it.
Short for apply.
Yes.
I like brackety splat.
Brackety splat. Yeah. Well, I'll be using app, and then I'll just be calling the $sign fmap, and visually it's different, but it is fmap. So the first law says that pure id app v is the same as id fmap v, which is just v. So if you have a pure id, which says that if you have a pure f and a pure x and you app them together, you just get pure f of x. So what that's saying is that app doesn't introduce side effects if they aren't there. So you have an effect-free f and an effect-free x, you get an effect-free f of x. So you can think of the app as the $sign operator, the application lifted into the applicative context. Interchange is an interesting one. Here we have, this is our first law where we have a potentially impure left-hand side, which we're calling u. And we're saying that u app pure y is equal to pure, and then $sign y is the function that takes a function, such as u, and applies it to the argument y. I have all the type signatures in the lower right, so you can look at that and see what I'm talking about. These laws are kind of hard to understand without the type signatures. What that's...
People ever draw commutative diagrams?
I'm sorry?
People who draw like commutative diagrams?
I think people probably do. I don't, because that's not how I think about these things. But I'm sure that people have. You know, I mean, there's a lot of category theory.
Yeah, there's a lot of like ordering related. It's easier to visualize sometimes.
Sure. So what this is saying is that it doesn't matter in terms of effects which side of the app the side effect is on. So if you only have one, you get the same side effects if your side effects are on the left-hand side versus on the right-hand side if the other side is pure. And finally, we have composition. And this law looks a little weird. But what it's saying, and we have the types written out here to make it easier to understand. I'm using K instead of an F for the applicative type. So it's an applicative K. What it's really saying is that the composition of applicatives is associative, as is also true of functions. So it doesn't matter which order you associate your functions in. Now, if applicative had do notation, or if you have an applicative that's also a monad, you can represent f app x as follows. You're doing pure fun, which means your pure fun gets f. So whatever side effects are in f happen, and then you get a pure value. Whatever side effects are in x happen, you get a pure x. And then you're returning the pure function applied to the pure value. And that's how applicatives that are monads work. That function for a monad is actually called AP, which is the same thing as the applicative app. It just has a different type constraint. So the takeaway is that we can view an expression like this, where we have this chain of apps, f app x1, app x2, ... as a computation that first it evaluates each of those elements with the side effects happening in left to right order. And then it returns f star, where f is the result of evaluating f, applied to x1 star, which is the result on, where you evaluate the subterms before you put them into the main function. That's how that works. The role of the $sign, which is the f map, is that often your outer function will be pure. Sometimes you do want your outer function to be in a computational context, but usually the outer function itself is pure. It's always the same. And so that's why we'll use f maps. We use this f mappy thing a lot. We have what I would think of, what I might call, I have no idea how to pronounce these, but they're one-sided apps. Unlike unlike app, the star in the angle brackets, the left-pointed, I'll just call that.
Propose left flake and right flake.
Sure, left flake and right flake. Let's do it. Left flake takes two applicatives, and it will execute the side effects of both, but then it throws the value from the second away, as you can see from the definition down there. Like, that's how it's defined. And the right flake will execute both of its arguments for side effects, but the middle term returns an integer because it reads digits until it doesn't have any more digits to read, uses read to convert that to an int. And then the last element, or the last piece of that chain, returns the closing square bracket. My parse2 uses inside. There's a type class called alternative, which is a stronger version of applicative. It has an empty and it has a choice operator. The empty is something that lives in that applicative, and the choice favors the first one. If the first one fails, it'll run the second one. So if it looks like a monoid, that's the right intuition. And it can be similar or it can be different. So alternatives behavior is determined by what is the empty value and what is the choice operator. And usually empty is supposed to be recoverable failure. And then A1 choice A2 is try to do A1. If that fails, try to do A2. But favor A1. And some and many we'll get back to, but this is how they're defined. And notice that they're defined in terms of each other. Some will return a cons. Some p will return a cons of a p and then many p. And many p is a choice between some p, which means that it can do more p's if it wants, but if p fails, it'll return the empty list. So what they actually mean is that some p is going to execute that p, which is going to be a parser, until it fails, and it will succeed if there's at least one success. And many will succeed if will also succeed if there are no successes. But let's talk about some simpler instances. So with list, we get the very boring empty is the empty list and choice is concatenation. That corresponds to multiple value functions where failure is returning nothing, saying I found nothing that meets these constraints or nothing that works. And concatenation is the choice. You're deferring that choice to later in a lazy list. Excuse me. Maybe is an alternative with empty equal to nothing. And if you have two justs, then you favor the first one. Or another way to say it is that once there's a just, you can just ignore the rest of the choices. So for a parser, this is where it starts to get interesting. Recall that our type for a parser is it takes a string and it returns maybe an A and a string, which is the rest of the string, what hasn't been consumed. So empty is the parser that just always fails. And P1 choice P2 is represented as the function that takes a string. If P1 succeeds, it's done. If it fails, then it tries P2. And some and many are not especially useful in alternatives like list or maybe, but they're very useful in parsers because you continually run an applicative effect until it fails, with the assumption being that it will at some point fail. And so many P will run that applicative effect until the first failure and succeed with the list of values drawn. Which means if it fails the first time, it still succeeds. If P fails, many P will still succeed. It'll just return an empty list. And yeah. Now, the alternative, or the sum and many for list and option are not useful because there will never be a failure. Like it's a computation that will not change its dynamic. But with parsing, you know that eventually you're going to run out of string. So for an example, here's a parser. We have a parse digit that returns a digit character on success. And if it doesn't see a digit character, then it fails. And parse int is built on top of some parse digit. So it has to parse at least one digit. It gets a list of digits from the sum, and then we fmap read over it, which is how we get an int instead of a string. Does all of that make sense?
I have to let that one bake
Sure.
for a little bit and read that slide. Read those slides like 10 more times.
Okay. Is there anything that's like not clear, or is it just that there's a lot of information to absorb?
Yeah, I think it's a lot to absorb, and I don't think I'm good enough at reading Haskell type signatures to to really grok it all.
Okay. Well, alternative is going to become useful when we do the second lab, and that's why I'm teaching it now.
Yeah.
But you're probably going to get a better sense of it when you actually have code to look at that uses it.
Yeah, I think practical examples is gonna make it's gonna solidify everything. I'm very excited for that.
Sure. So the next thing is the monad laws. We have a left identity law, which says that if we have a return of x, which is a pure x value, and we bind it into a g, we get g of x. The right identity says that if we bind a monadic value that's an MA into return, we get the same MA back. And associativity says that M bind G bind H is M bind lambda x to GX bind H. And presented like that, these laws are not very approachable, which I'll admit readily. I didn't understand them either when they were presented that way. So there are two ways to approach these monad laws and to get a sense of what they really mean and what they're telling us about monad. The first is to convert into do notation, and that'll sort of tell us as an imperative execution context, what they mean. And the more rigorous one, which I actually prefer, uses what's called the Kleisli arrow, which isn't as scary as it sounds. So in do notation, the left identity law is saying that if we have a do block and x prime gets return x, and then we apply g to x prime, it's the same thing as applying g to x. So that's a simplification. It's saying that return doesn't really do anything other than lift something into the monadic context with no side effects. Right identity tells us that if we have x gets m and then we return x, so we're putting it back up into a monad, we get the same m back. You'll actually see in novice code, sometimes people will have this construct where they assign something monadically to a variable and then return it. And then the third law just illustrates that you can compose monadically. So you have this x gets m, y gets g of x, where the x came out of the monadic value m, and you're returning x, or you're ending with xy. I don't want to use the word return because h of y is already a monadic value. It's equivalent to that with the nested do blocks. But my confession is that I didn't really understand the monad laws until I was introduced to the concept of the Kleisli arrow. And a Kleisli arrow, you can think of it as a function-like computation that has access to a monad. So the Kleisli arrow of a monad M is the function type A arrow MB. Or, it's like saying A to B, except I can also access this monad M. So some Kleisli interpretations. String to maybe int is saying I take a string and I either fail or I return an int. Node to list of nodes, that's like a graph search or something, is saying I take a node and I return multiple nodes. I haven't really gotten into STM, but it's software transactional memory. It's a way of making mutable state that is thread safe and has a lot of nice concurrency properties. Key to STM value is saying I take a key and in an STM transaction, I return a value. And finally, string to IO bool is saying I take a string, I have arbitrary IO privileges while I execute, but I'm going to return a bool. And the reason for this is we're interested in the computational context and which changes can happen. And we're usually thinking about computations as function-like, but with a little bit more, a little bit of state, a little bit of IO. So you can think of A arrow MB, that's the Kleisli arrow on M, as a computational step in an M context. And when you have just a bare MA, there's no function, you could think of that as isomorphic to unit arrow MA. And in fact, in a strict language, a stateful, something that's evaluated, something that's stateful, but not typically a function would be like either a zero argument function or a function taking unit in OCaml. So you can think of it as isomorphic, but because Haskell's lazy, you can just throw out the extraneous unit. Okay, so I have no idea what to call this operator. I'll just call it Kleisli arrow, or Kleisli composition. It takes an A to MB, a B to MC, and it returns an A to MC. So it's the monads analog of the composition operator. And the way it works is it takes That is correct, isn't it? Yeah, it becomes the function that takes an A, turns it into, I think that's right. I'll have to check, but it's the monadic analog of composition. And with this, we get much cleaner monad laws. Left identity and right identity are essentially saying that return is the Kleisli arrow, and it's a Kleisli arrow from any type to itself that doesn't do anything. Return Kleisli composition G is just G, and M prime, which could be anything. Kleisli composition return is M prime, and the associativity means that when we have this Kleisli composition, it doesn't matter. When we have a Kleisli composition, a chain, it doesn't matter the order in which they happen. Okay, so if you want a sense of how monads and applicatives and functors differ, you can look at their sort of fundamental combining operation. So fmap takes a pure function and a container, and it applies it to the container. While applicative allows that function to be in a computational context as well. And finally, monad, if you look at it there, is allowing, that's the reverse of, or that's the flip of bind. So this flip bind operator, rather than taking a value in a context, it takes a function, it takes a Kleisli arrow, and it applies it to the monadic container. And what that means is that your intermediate values, your A's, not your F's of A's, but your A's, can influence the evolution of the future evolution of the computation. So here are some monadic functions that you'll see. One is join, and if you didn't have join, you could write it just by binding to id. And what that does is if you have two or more levels of a monadic type, you can reduce it all the way down to one. So if you, one way to think of this is if you have an IO of IO event, that's the same as not, or that's equivalent to an IO int, because you're not getting more information by saying, oh, it does IO to produce the IO event. Join in the maybe monad will take nothing to nothing. It'll take just nothing to nothing, and it'll take just x to just x. So again, it's sort of flattening a nested maybe. And join on the list monad is just concat. On the state monad, you have two levels of nesting. So you have a stateful action with state S that returns another stateful action. And the way the join works is it just says, okay, whatever state you get, I'm going to run the first stateful action. That's going to return another stateful action. I'm going to run that with the updated state. And the join in IO is kind of the same.
So if you have the concat method, the concat method being a method how you join like a list, right? That would require everything inside to explicitly state how to concatenate it. Like if you have like a list of integers. Right?
Well, join takes a list of something.
Oh, so yeah.
And returns a list of that.
It's not a list of, okay.
Right. The thing about join is that you can get down to one layer of that monad, but you can't get any further down.
Which is why
so you can go from IO of A to IO of A, yeah. But you can't go from IOA to a pure A.
Yeah. But like if you have a list of strings, that's you can join them with. Never. Just thinking about.
Well, yeah, you could join them into one string only because string is a list of char.
Kidding.
But if you have a list of ints, then you can't.
Yeah. So like in many other languages, this would probably be implemented by like some sort of complicated like full, where they just
right.
A loop and then like correctly structured the body of the loop to implicitly be performing the join. But you can't join a bunch of stuff and then hold on to it and then use it later.
Yeah.
And enter this searching for keys and deeply nested hashes, right?
Yeah, exactly.
So some other monad functions, there's a monadic analog of filter M where you pass a Kleisli arrow A to bool or A to M bool, and you get a list of A to M list of A. Again, that's a Kleisli arrow on the left, and A arrow M list of A is just another Kleisli arrow. Fold M is likewise a monadic or an effectful fold. And the nice thing about the Kleisli construction is that you only need a monadic type on the last argument, because you can, with this B arrow A arrow M B, you're essentially saying, okay, it's some functional value. It takes a B and takes an A, and all of the monadic actions happen in producing the next B. So it allows you to, that's sort of the magic of currying, is that you can say, okay, all of the effects are in producing the return argument. And then there's a zip width. Forever is a function, it takes a monadic action and it just repeats it forever. It's M sequenced with forever M. When it takes a condition, which has to evaluate to a bool, and a monad that returns a unit or a nothing type. And if the bool returns true, it'll do the action, and if it returns false, it's just going to return unit. It's not going to do it. And in 710+, when it applies to the applicative, so you can use it on an applicative regardless of whether it's a monad. And that doesn't break monad because all monads are applicatives. We have lift M2 on up to 5, which take pure functions and lift them into monadic context. So sometimes you have a bunch of monadic values and you want to apply a pure function to them, and this is how you do that. And you may notice that lift M1, or it's just lift M actually, is just fmap. I think lift M was grandfathered in before people realized that every monad should be a functor.
Why does it stop at 5?
Just arbitrary. You have to stop somewhere.
But like, I feel like if you want to like, because that's just like applying 5 functions.
No, it's a 5-argument function and then 5 monadic values.
Oh yeah.
Yeah. But you could write lift M6 if you needed it.
Yeah.
Let me just correct one thing here. App is exactly like the applicative app. It takes 2, except on a monad, it takes 2 values. Or it takes a function and a value, evaluates, or a monadic value containing a function and a monadic value around the x, and it will evaluate both and then return f of x.
Do the monads, okay, so you said it takes a monad surrounding a function and a monad surrounding a value and returns a monad of the same type of those two?
First of all, I should say a monad surrounding a function type, because there could be multiple functions in it if it's the list monad.
Okay, so a function type, but you can't have a like the monad that surrounds the function type wouldn't be the same type of monad that surrounds the value, would it?
No, and the type signature reflects that. It takes an M, A to B, and an MA, and it returns MB.
See,
it's the exact same thing as the snowflake on applicative, except on a monad. And again, it's grandfathered in because this exists from before all monads were applicative.
So you're just applying the function inside the first monad to the second one and giving you what, the second monad back? A monad of the second type, a monad of the thing that's
of the B type.
The B type.
Yeah.
Back with that function applied to it. That's
yep.
Seems like conceptually unsafe for some reason.
No, it's perfectly safe. I mean, it can be confusing depending on the monad. because as I discussed before, like with lists, the monadic do notation is list comprehensions. So you really don't have one value being, you're not getting one F and one X, you're getting a bunch of Fs and a bunch of Xs when you're using the list monad. So yeah, this is complex stuff, and it takes a while to get. I'm just hoping to present it, make it accessible. So the reader monad, we've already discussed that a function type on a known type R is a functor, and that it's an applicative. It's also a monad. In this case, we have a new type around it, and so reader is a constructor. It takes an R to A, and it returns a reader RA, and run reader just inverts that. It just gets the function out of it. What it represents is an action that returns an A and can depend on read-only state. So like a configuration file, or not a, well, like a configuration type. And here's the definition. Return X, as you might expect, is the reader that doesn't read the configuration. It just always returns X. And then to do RA bind F, that's the reader that first it runs RA, because that's an action, with the reader state. That gets you an A. It applies F to that, getting you a reader RB. And since that's a reader action, you have to use run reader to get the function out. And then you have to pass in the read-only state again. This is what I call the bare reader monad. This is what it would look like without the constructor. Sometimes it's easier to see what it does just by by getting rid of the constructors. Ask lives in every reader type, and it's a reader RR. So it returns in the same type as the state, and it just returns the whole state. That's like the first thing you might want to do with a read-only state is, I want to know the whole thing. Well, that's what ask gets you. So we have a data type called config. It's got an in file, an out file, and a limit. Limit is an int. And we have a reader action. So it's an action in the reader monad. Limit check n is going to return the action that first it asks what the config is, and then it compares the n to the limit. And if n is less than or equal to that limit, it returns true. Otherwise, it returns false. So for example, when we do limit check of 600, we get an action in the reader monad. It's not yet a value. It's, okay, I know what to do once you pass me a config that I'm reading from. And then if we do limit check 450 and pass that into the run reader function, that's just infix notation up there. And we give it a config where the limit is 500, it returns true, because it says, okay, now that I have your config, I know that this limit check passes. Asks is kind of like ask, but you pass in a function with it, which gives you sort of a view on that state. It's R to A for some other A, and it returns F of that state. So for example, asks limit is the function that returns the limit, or it's the reader action that returns the limit of the config. So in the upper right, we have asks in file, which is an action in the reader monad that returns a string. So it's a reader config string, and then we give it the config that we have with in.text, out.text, and 500, and it returns in.text. Local takes a function on reader states and a reader action, and it returns the reader action that operates on an updated state. So for example, when we do local on the function that takes a config and sets its limit to 1,000, and then we do limit check 750, because the new reader state or the new config state has a higher limit. When we run that reader on the config, it returns true, because the local function says, I want a reader action that changes the config before it reads from it. The writer monad, by the way, these are kind of hard to describe, but when you look at what they actually are, they're pretty simple. Reader monad is just a way of saying, I want to create values that are dependent on read-only state. And the way you do that is by, instead of passing around values, you pass around functions from that read-only state to a value. Writer WA represents the computation of an A with an annotation of type W. And type W is almost always going to be a monoid. It almost doesn't make sense to use writer if it's not a monoid, because for one thing, you don't get a monad. When W is a monoid, I'm sorry, writer R, that should be W, let me change that. Writer W is a monad. So return X is going to be the writer that gives you X, and since it doesn't do anything stateful, it returns the empty in that monad W. And the bind of a writer stateful action to a function, and again, that function is a Kleisli arrow, so it's a function that takes a pure value and returns another type in the action, is going to be formed by letting a pair W1 be formed by getting the pair out of the first writer action. So just using run writer, and then we take the A, we apply F to it. That gives us another writer action. We use run writer to get out the pair, B, W2. We throw out the A, we return the B, and our log, because that's what writer is really about, is it's about an append-only log. So we append W1 to W2. And this is the bare writer monad, where I've thrown away the constructors and just shown it as a bare type. And this would also work. This is a little more terse. There are actually a lot of writer functions. I'm not going to go over them today, but I'll just go over a couple of them. Tell is probably the most important one. Tell is your action that doesn't return anything. So the return type is unit, but it writes something to that log. So tell W is the writer that will not return anything, but it adds a W onto the log. Listen is a way of getting that log up into the value level. So you call listen on a writer action, and you get the version with you get a pair with the value and the state of the log at that point in the computation. Sensor and pass and listens I'm going to pass on, but you can look at them in the slides. And run writer and exec writer are functions that take writer actions, that is a writer WA, and get concrete values out of them. So run writer just says, okay, look writer, you're just a pair of an A and a W, and that's what I want out of you. I want the final return and whatever you've accumulated in the log. An exec writer throws away the value and just returns the W. It just returns the log. What's amazing about all this is it's hard to explain. It sounds probably like gibberish, and yet when you start using it in a monadic context, it'll do the right thing. So when you have a writer monad and you start saying tell do this, it will construct the log for you in a way that would be a huge pain in the ass to explicitly thread it in. And that's really what it's for, is the do notation allows you to do explicit state instead of implicit state, but it does all the plumbing for you. So here's writer in action, because it's kind of a complicated thing to talk about without showing an example. So collat's step. So the collat's conjecture is that if you take the iterative process where you start from an integer, if it's odd, you triple it and add 1, and if it's even, you have it. So for example, 201, it's odd, triple it and add 1, 604. That's what's at the bottom right. Then you have it because it's even, you have it again because it's even, you get 151, it's odd, so you go to 3n plus 1, 454, have it, 227, 3n plus 1 because it's odd, 682, have it, 341, 3n plus 1 is 1024, and then you can just keep having it until you get down to 1. The collat's conjecture is that every number gets to 1 eventually through that process. So there's nothing that diverges and there are no cycles. A single collat step, what it does is it writes to a log, which is a list of integers, a single element list of that integer. It says, I'm going to tell the single element list n, which means I'm going to put it into the log. And then it does the main work. If n is even, it's going to return n div 2. And if n is odd, it's going to return 3n plus 1. And then collats is a loop built on top of this collat step. So that's also, it takes an int and then it returns a monadic action in the writer monad, which doesn't return anything, but it builds up a log of everything that it's every intermediate step. Finally, the state monad. This is the explicitly threaded state. State SA is an action that returns an A and has read and write access to a state of type S. So these are the probably familiar at this point return and bind definitions. Return X, doesn't change the state and just returns X. And a stateful action that returns an A bound into an F is going to produce, I need to, as written this one, type check. And it's going to return a stateful action that takes the state. First it runs the SA on the initial state, getting an A and an S1. It throws the A into the F that is being bound into. That gets you a new stateful action using run state again on the updated state, that is the post-SA state. Or S1, you get a B value and an S2, which is your new state. That's how the bind works. So you're sequencing the operations. Nothing really new. Gets and put, we went over in lecture 6, so I'm not going to go over them again. Modify and modify prime are passing in a function that will change the state, and modify prime is just a strict version of that, so you don't have func buildup. Run state is how you get that function, the S to A pair S, out of a stateful action. And eval state and exec state are variants that the eval state just returns the A, so it throws away the final state, and exec state just returns the new state. I have to go for about 2 minutes.
Learn you a Haskell website. There's a lot of kind of illustrative examples of why this stuff matters.
I found an a 99 Haskell, like 99 problems in Haskell.
Oh,
To
yeah.
like go from simple to
Yeah, 99 problems, but a monad ain't one.
yes. Don't edit that out.
Don't edit that out, leave that one. We've been talking to your future self,
Okay.
so you're gonna hear it to edit it.
Yeah, I was about to say if there's a conversation about how weird I am going to hear it in the post editing. So, a val state and an exec state. The first gets you the value computed but throws away the state. The second gives you the new state, but it throws away the value that's been computed. Map state allows you to take a function that takes a value and a state, returns some other value, some b, and an updated state, and you can stick that in after. So it takes an f, which is a function on the a being computed and the state, and it sticks it in after the state now. And by the way, if these functions are a little confusing, just remember you can always write your own stateful, and you can always write your own state actions and your own writer actions and all of that. I actually had to look a lot of these up. Like, these are new to me. With state allows you to, it's kind of like local on the reader. It allows you to pass in a function and a stateful action, and it will give you that action on the updated state. And the update happens before whatever the state in M is. There's like no way to talk about this stuff that isn't confusing. A lot of it's just playing with it. But, you know, it's better to work in the state monad if you can than in I/O where anything can happen. So, monad transformers is a hard topic that we will begin to approach. Another thing that if you don't get it in one sitting, that's fine. It took me an embarrassingly long time. So first, let me talk about motivation for monad transformers and really what they are. So when you have functors, they compose. So for example, list is a functor, maybe is a functor. And a list of maybes has a natural functor. We have a new type compose. Compose GHA is a wrapper around G of HA. So H and G are both container types. So for example, at the bottom, we have a compose of, and we feed it a list of maybes, and the compiler is smart enough to say, okay, so G is list, and H is maybe, and A is some numeric type. And you apply fmap +1, and it just works, which is great because functors compose naturally. There's only one way to compose a functor of a functor into another functor, and it's wonderful. This is what fmap looks like on compose. So the fmap on the composite type is the fmap of the G given the function, given another fmap, which is the fmap of the H, of the f that you're fmapping across the composite type, all of that applied to the x. So yeah, that's kind of cool. The same is true of applicative. I haven't derived it here, but there's a natural applicative for the composition of two applicatives. But for monad, there's not. And that's actually a problem because, like, I talk about readers, I talk about writers, I talk about state, I talk about I/O. But in a real application, you might want to have two different kinds of stateful effects that your monad can do. You might want to say, I can do STM and I can also write to this log or something like that. And sometimes you can do that and sometimes you can't. So what we say is that monad doesn't compose. And what that really means, it's not that you can't compose monads, because you can, but you're not going to get another monad back necessarily. And the easiest way to show why that's true is to consider join. That's a fundamental thing that you can do on a monad. If you have an M of MA, you can turn it into an MA, and there's a natural way to do it. If we think of monads as representing computational capabilities that are available when you're computing that A, it kind of makes sense. For maybe, that capability is early exit, it's failure. I get a nothing, I'm done, computation's over. For read or R, it's access to read-only state of type R. For state S, it's access to read-write state of type S. And for I/O, we're saying, okay, all of the capabilities of the machine are available in computing this value. And join is valid in a monad because M of MA and MA have the same computational power. You can't do anything more in an I/O IOA than you can do in an IOA. And let's look at list to get a little bit more into this. A list of ints and a list of ints, they're not really the same thing. The list of ints has more structure. But in the computational context of multiple values, the sort of logical computing, okay, these are the possible values here, these are the possible values here, let's branch out and see where things meet. In the multiple value context, they're the same thing, because a list of ints can be reduced to a list of ints that has all the same values in it. So now let's talk about restricted I/O monads, which is something I haven't gotten into, but you can create a restricted I/O monad that can only do some of the I/O using module boundaries and some things like that. And we have YA, which the only I/O it can do is put the character Y to the console. That's the only I/O privilege it does, and then it returns an A. And ZA can put char Z's to the console, but it can't do anything else. Now, if compose YZ were a monad, then we'd expect that Y of Z of Y of Z of A has the same computational power as Y of Z of A. But that's not true. Because Y of Z of Y of Z of A, that means I print out some Y's, then I return a Z of Y of Z of A, then I print out some, which, that thing is saying I'm going to print out some Z's, I'm going to print out some Y's, and then I'm going to print out some Z's, I'm going to return an A. So that could print the string YZ, YZ. Whereas Y of Z of A, it can't, because it prints out a bunch of Y's, it prints out a bunch of Z's, and then it returns an A. So another way to look at this is to say that monads don't commute. Y of Z of A is not the same computational context as Z of Y of A. One can print out a bunch of Y's and then print out a bunch of Z's, and that returns an A. The other one can print out Z's and then Y's and return an A. And for example, let's look at the two ways of composing maybe and list. Maybe of list of A says, I either fail or I return multiple values. And that has the power of early exit, because as soon as you get a nothing, you're done. The other alternative, M2, is a list of possibly failing values, which is a different thing. It's can represent things that, they represent different things. What's up?
So all monads are functors,
All monads are functors.
but you said functors commute.
They don't commute. They compose.
That's what I meant, sorry.
The composition of two functors is a functor. The composition of two applicatives is an applicative. The composition of two monads is an applicative because they're applicatives, but it's not necessarily a monad.
Okay, so you don't, okay. But isn't there like, never mind, gotcha.
Now, some monads do commute, and that's actually pretty interesting. Because if we think of monads as adding computational capabilities, if those capabilities are orthogonal, they don't interact with each other, then the monads do commute. So there's a language called PureScript. It's the Haskell community's answer to the browser. essentially. They have what's called an F monad or an effect monad, which uses something called row typing, which Haskell doesn't quite have yet. I mean, you can create it using language extensions. I might get into that later. But the F monad is parameterized by all the effects that it can have. And so you can build up a value and it'll say, okay, this has access to canvas and it has access to random number generation and it has access to the console. And since those things don't interact with each other, because they're orthogonal, you can treat the monads as commutative.
But only ones that have the same capability.
No, only ones that have completely orthogonal capabilities.
Oh, I see.
Yeah. So what we have is that f of g of A isn't necessarily a monad just because f and g are. So what we actually end up working with is what's called a monad transformer. And those are higher kind of types that take a monad called a base monad and transform it into another monad with more capabilities. Before we get into monad transformers, we should look at the identity monad, which is actually the simplest monad there is. It's just a new type. Identity is the constructor into the identity monad, and run identity pulls something out of the identity monad. And it doesn't add any capabilities. And identity A is isomorphic to A. It's the same type, but with an identity wrapper around it. And the reason we might want identity is because if we want to turn a monad transformer into a monad, we just apply it to the identity monad. And I'll show some examples. So I've talked about reader and writer and state and how one might define them. How they're actually defined is with monad transformers. So we have maybe T, which takes a monad M and an A, and run maybe T is an M of maybe A. If you do maybe T of identity A, you get an identity of maybe A, which is isomorphic to maybe A. And you can see the same thing happens with except T, which is for either, where the left case represents error. Now, by definition, the actual reader and writer and state monads are reader T, writer T, and state T applied to the identity. So if you want a reader capability and a writer capability and a state capability all in one, you can stack monad transformers. You can say, I want a reader T some R around a writer T of some W around a state T of some S around identity. That probably sounds confusing, and it kind of is, but what were you gonna ask?
Why do you need an explicit identity monad? Because I mean, every value is sort of can be. I mean, I feel like that would be something that Haskell would have done for you. Is every value would explicitly be its own identity monad, or implicitly be its own identity monad.
You mean every type?
Yeah.
Okay, so the reason not is the kind system. So reader T takes an R, which is a base type. It takes an M, which is type arrow type. So it's already taking a type constructor. So if you want to apply it, if you want to apply something that takes a type constructor to a concrete type, you can. Let me back up. Okay. So monads don't compose.
Yes.
But if you have, a bucket of things that convert one monad to another with more capabilities, then as long as you start with a monad and you put a transformer on top of it and another transformer on top of that,
yep.
We call it a monad transformer stack,
yep.
You'll still have a monad.
Yep.
We need a base monad.
Mm-hmm.
And like all monads, it has to be type arrow type.
Yep.
Now, we want our base monad to not have any special capabilities, but we still need a type arrow type. And the type arrow type that doesn't have any capabilities would be a wrapper, just a new type, like it's just a wrapper.
Yep.
So that's why we have the identity monad.
Identity is the wrapper that does nothing.
Exactly. It doesn't add any capabilities, but it's a monad.
So okay. I feel like identity is just a function of being a thing. You get an identity by being something. Like you don't need an explicitly defined identity that does nothing. Like if you have something that is a base type, any type really, you can be comfortable that it is what it is. So you should be able to compose. You should be able to transform anything. That's why like lifting something into a monadic context always works. It's because you can always go from a base type to a monad that does nothing, which means my point is, would you have to like? I guess I see like so that you can work with like things that aren't monads if you don't want to, but
Sure. So the monad transformers by design take as an argument a monad.
Yeah.
And because they require a monad, because they're operating on a container type already, a type arrow type.
Yeah.
When you want your base to be, they don't operate on types.
Oh,
they
I
operate
see.
on containers.
because like if you're not working with monads, you don't want your base types to be type arrow type. You want
Right.
it to be like a concrete type.
Identity is your most boring container ever. It holds exactly one thing. So state is actually derived from state T, which is the monad transformer. So what actually exists in the monad transformer library is the state T that's a wrapper around S arrow M A pair S, where M is some monad, and state is just defined as the state T transformer with an S applied to the identity monad. And there's a function called state, lowercase, that will take an S arrow A pair S and turn it into a state, and it'll do all the wrapping for you. And then run state will do all the unwrapping for you. So you rarely have to do explicit unwrapping, which is nice. Because I'll be honest, there's a lot of type class magic that makes monad transformers not hell to work with. And if it didn't exist, and you had to work with like multiple levels of abstraction, the stack of like 3 or 4 capabilities, and you had to, it would be a nightmare.
Yeah, like if you had to traverse it to get out.
Exactly.
Like what you
Exactly. And sometimes you do, but often you don't. And that's why monad transformers are useful. Because if you had to always do that, people would just not use them. They'd just use I/O for everything.
Wouldn't it be possible to transform every monad to the identity monad of its element because every monad has to have a return? So you could easily join. You should be able to join any number of arbitrary monads.
I'm thinking. Because
But I guess you wouldn't be able to.
it wouldn't be useful. Like, for example,
You don't know which monad would be wrapping what you got back.
well, the reason it wouldn't be useful is that there's no reason to, if you have an IOA, there's no reason to turn that into an identity IOA. The identity exists not because it's a useful monad, but because as a base of a monad transformer stack, it's saying, okay, I want my base monad.
Well, so I guess what I mean is if you had a list of IOs of A,
Okay, we have a
Right.
list of IOs of A.
and every IO has, oh no, that's wrong. I'm thinking like there's always a way to get at what's wrapping A, right? You could retrieve A.
Wait.
No, you can't. Never mind. You sort of can, but you can't. I'm thinking like you could turn a list of IOs of A into a list of A's,
No,
but that defeats the whole.
but
purpose.
you can turn it into an IO of a list of A's. That's what the sequence function does. You can take a list
There we
of
go.
stateful actions and you can get the
Stateful.
stateful action that returns the list.
Yeah.
But you can never throw away the fact that it's stateful. You can never, unless you use this function that you should never use called unsafe perform IO. I shouldn't say you should never use it, but you should almost never use it.
But you can index into an array.
Yes, not all monads are impenetrable.
Okay.
Because
But
like
it's just not a guarantee of being one.
no, like so the state monad, there's the run state. You call run state to get that function out, S, the function that takes an S and returns an A and a new state.
Yep.
You call run state, you give it a state, and you get pure values. The IO monad itself, you can never go to a pure value. So some monads, they just encapsulate the thing forever.
Yeah.
Other monads you can unpack. Like a maybe monad, you can just use a case expression.
Okay.
All right. And also, indexing a list isn't technically pure because you can go purely from a list and index to a maybe.
Yeah.
But you can't go to an A because that index might be outside of the bounds.
I think that's why most languages choose to panic if index doesn't exist, so that
Mhm.
like all of your array options don't involve you also making case statements against.
But throwing exceptions is stateful. Although there is a
Oh, I'm not a fan, but yeah.
there is a functional go-to called cont or continuation monad. I'm probably not going to cover it. Maybe I'll cover it late in the second half.
Mhm.
But there is a purely functional go-to, which is kind of neat. Although I'm hesitant to use it in real code.
Yeah.
In any case, these monad transformers, by adding these capabilities, they can create complex types. So for example, we might want to wrap state TS around an IO. We're saying, okay, this is IO, but it also has access to this in-program state of type S. And then you get S arrow, IO, A pair S. And that kind of makes sense. You know, you're saying, I mean, it's a Kleisli arrow. So you're saying, okay, given a state, I'm going to do some IO and return an A and the updated in-program state. You wrap an except T around it, and you get S arrow IO either EA S. And these types start to look unwieldy, especially if you have 3 or 4 things stacked. So how does one actually make sense of them? How does one work with them? Well, let's talk about that. So first of all, there's lift. Lift, if you have a monad trans and a monad M, a monad trans T and a monad M. So for an exercise, think about what the kinds of all these things would be. It will lift your MA to a T of MA. So any T that implements monad trans gives you a way to lift something from the simpler internal monad to the transformed monad. Also, I mentioned ask, which gets your configuration out of a reader. I mentioned put, pass, these functions of the reader and the state and the writer monad. And I kind of lied, because ask is not anchored to a specific reader monad. It applies to any monad, that's M, that implements a type class monad reader. This is a multi-parameter type class, and I'll get to that in the second half of the course. For now, don't worry about it, just it's magic. Or you can look into it if you want. So the reader, state, and writer functions that I've presented, they're not functions on a specific type. They're functions that are written to type classes. And there's a package called MTL that has these monad transformers and the monads in them. And it ensures that if you stack these monads on top of each other, the capabilities compose, and you can write code that is a lot simpler than it should be if those type class conversions weren't happening for you. Now, this approach may not scale very well because you have to, essentially what it will do is that if there's a reader somewhere in your stack, and if all of your layers of monad transformation are proper monad transformers, then you will have the capability to use ask. And that requires, I'm trying to think of a succinct way to explain it. The lifting capabilities require having every monad transformer in the package aware of every other one. So you get O of n squared complexity. But the reason that's not such a problem is because most cases of in-program state are the reader, the writer, and the state capabilities. And if you're only stacking those together, another thing you can do is you can just use the RWS monad, which combines the three. So RWS is parameterized by a type R, a type W, a type S, and it says, okay, I have read-only state of type R, I have append-only monoidal state of type W, and I have read-write state of type S. And the reason I'm explaining this stuff is, I have no expectation that anyone can understand it at a deep level just by being talked to about it for 30 minutes. But you're going to see it in Lab 2 code, and I want you to know what it is. But you're probably not going to really understand it until you've worked with it, until you've seen it in other people's code. The reason I'm bringing up monad transformers is because if you look at the web frameworks, people who want to define a way of saying this is stateful, it has access to, let's say it has access to the request sent in. So you could have like a request monad. Well, they're actually going to write a request T monad, which is a transformer, and I'll leave it to you to decide, okay, do I want to transform the identity monad, meaning that I just have access to the request, or do I want to transform the IO monad, meaning I have access to the request and IO?
Do you think of CRUD apps as just an RWS monad on the database?
You could, yeah. Yeah, and in fact, that's an interesting question for a number of reasons. By the way, this is probably like the hardest thing I'm going to cover. After it's sort of, I've been going uphill. Things have been getting harder and harder and harder. And then now we're going to have the downhill where we start actually exploring things like Haskell and the web, or I could do high performance Haskell. The monad transformer stuff is really complicated. To be honest, some people don't like it. Some people just avoid monad transformer stacks. And you can get a lot done without them. But they are sometimes useful, and you'll see them in other people's code. With regard to what you asked, Rob, about CRUD apps, yeah, I guess kind of. When I think of the RWS monad, what I'm thinking of is where you have possibly multiple different notions of read-only state. You have some kinds of write-only state that are happening, and you have read-write state, and you want to clump them all together. Now, one thing that Haskell doesn't have is you can't stack a state monad with one type on top of a state monad of another type, because then your functions like get and put that require a state monad are going to say, well, which state monad am I doing? So you would actually have to combine all of your state transformers into one composite type.
There's a feature in Rust that's actually pretty interesting that I'm just wondering if there's an analog to in Haskell. Sorry, I talk about Rust like often. It's just probably
No, that's cool.
It's just one of the things that I
By
know
the way,
about. Which is that it not only it'll do. I mean, it's not type inference. It's sort of like a weak coercion strategy. So like say you have a type that is like, you have something like, whatever T. If you try and like instantiate, you say you create whatever that takes an error type, right? If you try and instantiate an error, if that can be converted to an error for you, right? Like if you've implemented the to error or for error you've implemented from your thing, it'll coerce that for you. Like, and that helps you from getting like bloated composite types. You just you implement a conversion, and then it'll take care of that for you. And so I feel like that's a middle ground between like not between being safe but letting you like, I know that this can be one of those, and I explicitly wrote how you can make it one of those. So like, how do you get around not having to make a bunch of composite states? Like, does it have anything like that, such that you can like not write composite types to deal with like?
Sure. Okay, so let's actually play around with this a little bit. So you're saying that you want to have access to two kinds of state, and you want. So I think what you're looking at. I'm going to try to REPL this. Wish me luck.
I'll tell you the simplest example that I have for
Here,
it.
let's what I think you're talking about is, for example, you have and then obviously, like if you do state Y, state Z, if you have something in that monad, it's not a monad, but if you have something in this monad, then you're never going to, you can't use like get, because get applies to a general state monad, but you sometimes want to get your Y and sometimes you want to get your Z. So I think what you would do is you'd say, first you'd specialize. You'd say let, oh shit, but you'd have to, what you'd have to do is create your own type class.
Yeah.
Called monad state Y and monad state Z, and then have a lifting where you can say, okay, if I'm composing these states together, I want to be able to access them both.
Which is sort of like, which isn't like the worst thing in the world. And usually I think that in a case like that, there's probably a design issue prior to you getting here. You know what I mean?
Right.
But
if you're stacking 7 monad transformers on top of each other, you're probably doing something wrong.
So the simplest use case the thing that you run into every day when you're writing Rust that has something like this is that often you're passing around results. Like you're passing around results, which is just an either.
Right.
But a result is typically like it's not the contract, but you would almost always have it as whatever the result of the function was or an error, right? And so your top level functions like that are just either results or errors, but all of your little specialized libraries and modules are going to have custom errors like bad this error, couldn't do this error, whatever. And so as long as you tell it how to convert, like how to, then like you can stack those all up and pass them around however you want. You can always, you can always basically like, I don't know how you might call it like a unwrap, like, but recursively automatically. So you would do in this case is you would say something like, like Y, like data, a Y can be a Z if, or to make a Y a Z, do this. And then you could just do whatever you want.
So what you would end up doing is, I'm just going to write comments because I'm not actually going to implement it, but you would do, you do it with type classes, and then you would have, so instead of then you'd have like a new type, YT is a state. I'm just guessing.
Yeah. I think the chances you're going to be able to, if you have a setup like that one.
And then you create instances that allow you to convert, you say, okay, YT, you have like an instance where if, you create the instances and allow it to, and tell it how to lift your capabilities up.
I think the chance that if you got something like that you're going to get anything meaningful afterwards is sort of nil anyway. So,
well, I think that one case where you have one case where you have a use for like a lot of different monad transformers is actually what PureScript is hitting, where you have a canvas, effectively like a canvas T, saying, okay, I want to add the capability of doing things on the canvas. And then a random T, which adds a random number generator, and a console T, and an exception T. And of course, you can create your own new effect types in PureScript. And I think that the PureScript F monad, which works really well for commutative monads, for orthogonal capabilities, that's going to be that's going to probably, that and row types will probably come into Haskell at some point. I think it's just too useful not to, especially because one area where I want to see Haskell jump in is on data analysis. And right now, the data frame concept is something that we don't really have to the same extent. We don't have statically typed data frames. But that's another topic entirely. I think, in general, what you end up doing is you take all your notions of state, all your notions of writing, and all your notions of reading, and roll it up into one big RWS monad.
Yeah.
And then the only problem is if you're taking monad transformers from multiple libraries and you're smashing them together, well then you may have to do some manual lifting, pun intended.
God. Lift with your legs, right?
Something like that.
So, like, if you have monad transformers that, let's say you stacked multiple that are readers, you have to manually lift out the one that you want to read from.
You want to write?
You would, if it would even, I mean, I think you can do it, but yeah, like if you have, yeah, you would, because it's not going to know. I think it's going to look at the outermost, but let me see. So, reader. Yep, no problem. This is probably going to be hideous. If it even compiles. Yeah, it uses the outermost.
Okay.
If you tried to do string, it would give you a type error because ask is going to say, I want the outermost, which is why you would roll them up. Instead of having that monad, you'd have a reader T in string. You have to say what you're asking for. So, yeah, this is an area of Haskell where I think the presentation is still very obtuse. I think that monad transformer stacks probably are not ever going to become a popular way of doing things. They're just, I mean, it took me a long time to fully get them and why they're interesting. And I think PureScript's effect monad is much more accessible.
How do they enforce the fact that all of those things don't step on each other, that they're orthogonal?
In PureScript?
Yeah.
I don't know. I don't know. Yeah, I don't know a lot about PureScript, to be honest.
I was wondering if they have some hard-coded rule set that Canvas can't fuck with whatever.
I think that when you think of capabilities, so when you're thinking about, say, the composition of, this versus maybe list of ints versus list of maybe int, they mean fundamentally different things, and it's important to get them separate. When you're only taking a capability approach, when you're only thinking of capabilities, then there isn't much demand for I can do X and I can do this kind of capability and then I can do that kind of capability versus just I can do either type of capability, if that makes sense. Like there isn't much demand for I can do canvas effect and then I can write to the console versus I can write to the console or do canvas interleaved however makes sense. And by orthogonal, I mean, there's sort of a concept of pseudo-commutativity where, you know, let's say that I'm sending, if I'm sending you messages from the same person, like I'm an instant message client, then it's important that I get the messages in the right order. But if I'm sending a message from Bob to you and a message from Rob to Nicole, sorry, you're getting a message from a made-up person named Bob. It doesn't matter which order those events happen.
Right.
You know, it totally doesn't matter. So they're pseudo-commutative, or they're effectively commutative. So, all right. Thanks, everyone. Any more questions?
Thank you.
All right. We're done.